Okay, so Dan is in the room, we can start again. I guess we're sort of diverging a little bit from the math part of the undergraduate curriculum, and of course, every math major knows something about physics. And so today, I think we're going to hear about atomic structure. And it's my great pleasure to introduce my former colleague, Dave Benson, from the University of Aberdeen, now living under the shadow of the Royal Britannia, and he's going to tell us about nuclear.
Thank you very much. Can everybody hear me?
No, turn your eyes on.
Oh. Can everybody hear me now?
No.
How about now?
Yes.
Good, okay. Well, it's a great pleasure to be back in Athens, Georgia, after nearly 20 years. It's a great pleasure to be invited to give a talk here to celebrate Dan's birthday. So I managed to find a photo from quite a long time ago, and you'll notice that I've changed quite a lot, but Dan is essentially exactly the same if you look back then. I think there must be a picture in his attic that yeah, so this is also a much more modern one. This is from when I turned 60. Yeah, and what I'm going to talk about today is has to do with the one paper that Dan and I did actually write. So this, so the paper we wrote came out of a chance meeting in a record store in Charlottesville while I was visiting my daughter, and the name is Plan 9 from Outer Space or something. Just Plan 9, okay. So the theorem that Dan and I produced is called the Plan 9 theorem, and I'll get to that eventually. But what I want to talk about really is to advertise a notion called the nucleus, which is a part of the support that talks about no cohomology. So I've got to put on my glasses because otherwise I can't read what I've written here. So let's get to business. Yes, G is a finite group as usual. And actually, I'll talk about some other contexts as well, but let's start off with finite groups. And K is a field of characteristic dividing the order of the group. And M is a KG module. So, sorry? For the moment, it doesn't have to be, but it will be eventually.
Finitely generated graded, so that should be fine.
Sorry?
You're saying that would be a finitely generated graded commutative algebra.
Oh, I haven't got to that bit yet. Yeah, so the cohomology of the module is just defined to be X of the trivial module with your module. And it's a module of the cohomology of the group, which is just X of KK. And so the cohomology of the group is a finitely generated graded commutative algebra over the field. This is a theorem that goes back a long way to people like Evans, Benkoff, Gollard. And the thing to know about cohomology is that it only sees one block of the group algebra, namely the principal block. So we're going to decompose the group algebra as a direct product of algebras that can't be decomposed any further. That's a unique decomposition, not just up to isomorphism. If you then see where the identity goes in this decomposition, it's a sum of primitive central orthogonal idempotents. And so if I hit any module with these idempotents, it decomposes the module into bits that are in a block. So indecomposable modules are automatically in just one block. So you should think of a block as containing not just a part of the group algebra, but is a box for modules and so on. And the block that the trivial module lies in is called the principal block. And if a module is in a non-principal block, then it has no cohomology. So everything so far is pretty obvious, right? So also if a module has, there's one thing to know about finite group algebras, which is projective and injective are the same class of modules. And if a module is like that, then it has no positive degree cohomology. So you might wonder whether there are other modules in the principal block with no positive degree cohomology. So there's a very old conjecture, and I think it's due to Gashutz, but I'm not really sure. If someone in the audience knows, then maybe they can tell me. I couldn't find it in his work, but it might have been a word of mouth conjecture that says that if a simple module is in the principal block, then it always has cohomology. And this was investigated back in the 80s mostly, and is true for soluble groups. But then the question remains, what non-projective modules in the principal block have no cohomology? And the story I'm going to tell you came out of trying to understand this conjecture, basically, with John Carlson and Jeff Robinson. So we proved a theorem which characterizes those groups for which every non-projective module in the principal block has cohomology. So it turns out to be equivalent to the statement that the centraliser of every element of order P, where P is the characteristic, is p-nilpotent. So what p-nilpotent means is that there's a normal P prime subgroup of index a power of P. So it's basically a P group on top of a P prime group. And cohomologically, that just looks like a P group because you don't see the P prime group. So in the paper with Carlson and Robinson, we proved this when P is odd. And I finished the problem off with a different method for all primes. In the same paper with Carlson and Robinson, we actually proved quite an interesting fact about cohomology of modules, which is that if there's one non-vanishing cohomology group somewhere, I guess I should have said that n is positive here, not 0. Then actually there are an infinite number of different degrees in which the cohomology is non-zero. And in fact, there can't be any long gaps. There's a length that just depends on the group, such that there can't be any gaps that long. There was a nice little spectral sequence argument that proved that. So I discovered yesterday that I had misspelt nucleus in the header of this slide. So the nucleus, apologies for that. The nucleus is a certain subset of the spectrum of the cohomology ring. So the spectrum of the cohomology ring is something that was analyzed by Dan Quillen a long time ago. His description is in terms of the elementary abelian P subgroups of the group. So For an elementary abelian P group, the spectrum of the cohomology ring is just an affine space of rank equal to the rank of the group, of dimension equal to the rank of the group. And what you do is you just look at the normalizers of all the elementary abelian subgroups in G and twist, sort of fold up the affine space. So take a quotient by the action of the normalizer and then glue them into each other according to the inclusions and identify them according to the conjugations. So more formally, if you just have a category consisting of the elementary abelian subgroups and the inclusions, you take a limit, a colimit over those subgroups. So that's what I'm going to call VG. It's just the spectrum of that ring as analyzed by Dan Quillen. And so there's a definition of support for any module, but I'll just tell you how it works for finitely generated modules, because otherwise it would take an entire talk to tell you. If M is any finitely generated module, then we can make an easy definition of the support variety of that module as follows. You just take the tensoring with M map from X to KK to X to MM. If you think of X to KK as being Yoneda extensions, you're going to tensor this over K with M to get a Yoneda extension of M with M. Tensoring over K is exact, and so that actually gives a well-defined extension. And so you get a good map, and it's actually a ring homomorphism here from X to KK to X to MM. And the kernel of that is some ideal, and an ideal in a ring then defines a subvariety of the spectrum. So that's the definition of VG of M. It's just defined by the kernel of this map. So that's the support of a module. And if you take the supports of all the modules in the principal block that have no cohomology and take their union, it turns out that there's another way to describe that set, which is that you take all the subgroups of the group whose centralizer is not p-nilpotent, and you take the images of, so restriction goes from cohomology of G to the cohomology of H. So it defines a map from the variety of H to the variety of G. And you take the union of the images of the subgroups whose centralizers are not p-nilpotent. Okay, you'll notice that if you take a subgroup of such a group, it's still such a group because the centralizer will increase. And so you really only need to take elementary abelian subgroups, and you really only need to think about the maximal ones subject to this condition. So those two equivalent things are what we're going to call the nucleus. So it's a certain closed homogeneous subvariety of the VG. And so let me give you some examples to get some idea of what this looks like. For a p-nilpotent group, of course, the nucleus is empty. And for a group where the centralizer of every element of order P is p-nilpotent, the nucleus is just the origin. Now, you may not think it's appropriate to distinguish the empty set from the origin, and it isn't really when you're just considering modules, but later on, it will be important when I'm looking at cochains on classifying spaces. So I do want to make that distinction. So if all the centralizers are p-nilpotent, but the group isn't, then you want the origin. So I've given some examples here. If you look at small, simple groups, often their nucleus is just the origin. But as the groups get larger, of course, the nucleus is going to get bigger. So on the last line, I gave here a couple of examples of simple groups with non-trivial nucleus. In odd characteristic, the nucleus is always strictly smaller than VG. In characteristic 2, it can be equal. Quite strange fact. But here are a couple of easy examples to think of with non-trivial nucleus. If you take 2 cross A4, well, of course, the centraliser of that 2 is not p-nilpotent. And so the variety of that, of the inclusion of that Z mod 2 is actually in the nucleus. And in fact, it's exactly the nucleus. And another example is Z mod 3 cross symmetric 3. And I'll mention those examples again near the end because they're examples where we have actually been able to understand something. So those are some examples anyway. How are we doing for time? I have 50 minutes, is that correct? Yes, good. And I've taken 15? Yes, good. Okay, we're on track. Okay, so here's an example to illustrate what's going on for some particular group. So this group is cyclic 3 cross symmetric 3. So this is the structure of the projectives. There are just 2 simple modules. They both have dimension 1. They're basically the trivial module and the sign module. And they're glued together like this in the projectives. The projectives are 9 dimensions. And that's how they're glued together in a sort of diamond shape. And so here's a module with no cohomology. There's only one block in this group. So every module is in the principal block. So let's take just a left-leaning a slice from the bottom of the second projective. So if I take a syzygy of that, let's embed it in a projective and take the co-kernel. That's this other module. And then I do it again and I get back to the first module. So it's periodic of period 2. And there are no invariants in either of these 2 modules. There are no homs from K into either of these 2 modules. And so there's no cohomology. And that's typically how you get no cohomology modules. I mean, often it's easiest to construct just periodic modules and check a finite number of things. So here's the plan 9 theorem. So I bumped into Dan and told him a little bit about what I was doing with the nucleus. And he said, oh, should we investigate that for p-restricted Lie algebras? And so we did. We didn't completely solve the problem. I have to say it's still dangling out there. We solved the problem for restricted p-Lie algebras which come from semi-simple algebraic groups in characteristic big enough. So bigger than h plus 1, where h is the Coxeter number. And in this case, so what happens? The spectrum of the cohomology ring in this case is actually just the null cone in the Lie algebra. So this is the set of nilpotent elements in the Lie algebra. So it can be thought of as a subset of the Lie algebra. The cohomology ring is just generated by elements of degree 2 that form the coordinate ring of that null cone. And so in this situation, we actually worked out what the nucleus is. So we define the nucleus in exactly the same way. You take all the modules in the principal block that have no cohomology, and you take the union of their support varieties. And the support variety is defined in exactly the same way as it was for finite groups. And it turns out that that union is exactly the subregular orbit in that null cone. So it's the largest orbit closure that is not the whole variety. There's a unique such thing.
Closed orbit and orbit closer.
I guess it's orbit closure, isn't it?
Yeah.
You have to close it off. I mean, it's sometimes just called a closed orbit, but it means the closure of an orbit.
subregular will not be closed out.
Exactly. Yeah. And the proof involves some quite sophisticated machinery from the sort of algebraic group side of things. And then there's a remaining problem, which is there are lots of p-restricted Lie algebras that don't come from semi-simple algebraic groups. And what is their nucleus? You can define it in exactly the same way as the union of the varieties of the modules with no cohomology in the principal block. But I don't think we have any real conjecture as to what this is in terms of the structure of the p-restricted Lie algebra. If it comes from a group, by the way, is what's very clear is that the nucleus is actually invariant under the conjugation action of the group on the variety, which means there are only finitely many possibilities. Okay, so what about wider contexts? We can actually define the nucleus for any suitable triangulated category. We don't really have to. What's the problem with trying to define it for an arbitrary triangulated category? Well, the question is, what's the trivial model? We don't have one. So, I mean, for example, what we really wanted to know was what you do for non-principal blocks of a finite group, for example, and I'll discuss that in a minute. So what you do is you say, well, in the case of a finite group, we have an intersection theorem for varieties. So the variety of a tensor product is actually the intersection of the varieties. And one way of thinking of a tensor product is it's Hom from M to the dual of N. No, the other way around. Yeah, the other way around, yeah. But you don't really have to bother about the dual because a module and its dual have the same support. So you may as well think about Hom Mn. All right. So what you really do is the following. So you take a compactly generated triangulated category and you assume that you've got some Noetherian graded commutative ring acting on that triangulated category. So in the group representation case, the cohomology of the group actually acts on the stable module category. So what that means is this triangulated category has a center, which is the functors that commute with the translation in the category. But these form a graded ring, right? And it's in fact always graded commutative. So you've got a map from this graded commutative Noetherian ring to the center. The center need not be Noetherian. For example, in the stable module category, the center is not Noetherian. It's in fact huge and not Noetherian. Much bigger than the cohomology. But so you've got some sort of central action. So what this gives is for every compact object, we've got a map from R to Hom XX. And you can just use the kernel of that as an ideal and define a support. Okay. And so what you want to do is, if you've got a pair of objects where Hom between them is 0, you want to look at the intersection of the supports. So pretend that that you're forming a Hom object, which you can't form, and take the support of that. So really just take the intersection of the supports of the two objects. So in the case of the principal block of a finite group, this turns out to be exactly the same as what you do if you just have a trivial module. And the same in the restricted algebra case. So this is a definition that doesn't use the tensor product and doesn't use an internal Hom, but it defines a subset of the spec of the ring that's acting that you might want to think of as a nucleus. Okay, you happy with that? And then, you know, there are lots of strange questions like, is this Zariski closed even? I mean, in the cases that we've examined, it's Zariski closed. It was a union of a finite number of closed sets. But in general, it's not at all obvious. I mean, it wasn't at all obvious until we had that characterization in terms of centralisers, that it was closed in the finite group case.
So what the notation Hom star? Is that the X star?
So it's really Homs from this to a shift of that.
Oh,
So it forms a graded ring.
okay.
Is that clear? Yeah, good. Okay. So I mean, it can happen that Hom from one object to another is 0, but only because you haven't shifted it enough. Yes.
So we are only taking the graded module.
No, I'm taking objects in the triangulated category and taking graded Homs. Okay, so what do you do for non-principal blocks? So if you follow through what that definition gives you for a non-principal block, it does the following. A block has a defect group. This is a certain P subgroup of the group that kind of controls what's going on cohomologically in the block, and actually representation theoretically too. This concept goes back to Richard Brower, and I'm not going to define it for you. However, I mean, if you've got a module in some block, then its support is always contained in the image of the defect group, in the image of spec of the cohomology of the defect group in spec of the cohomology of the group. And actually what we want to do is use the cohomology of the defect group as our ring. Or not quite, we actually want to use the so-called stable elements. So this is a bit of a tricky construction. So Marcus Linkelman came up with this definition of the cohomology of a block. Remember, we haven't got a trivial module, so defining the cohomology of a block is not obvious. So you take the cohomology of the defect group, and then you take the conjugations inside that defect group that come from fusion of subpairs. And I'm not going to tell you what those are either, but if you want to find out, then there's a paper of Alperin and Brouet that does a thorough investigation of fusion of subpairs. And so inside the cohomology of the defect group, we've got these stable elements which should be thought of as the cohomology of the block. If you do that for the principal block, there's a theorem of Cartan and Eilenberg that tells you that you've got the cohomology of the group. Okay? So then he gets a map that factors through the Hochschild cohomology in some way that's not quite obvious, and gets an action of the cohomology of the block on the stable module category of that block. And it turns out that that's the right concept for trying to understand the support theory for that block. And so you now apply the definition on the previous page to that action of the cohomology of the block on the stable module category of the block. So you take the union over all M and N finitely generated in the block of the intersection of the support varieties of modules that have no X star, which is really this hom star that we were talking about on the previous page. Well, the hom star is actually the X hat star, to be honest. It's the Tate cohomology. But a module has no, I mean, there's no Tate X if and only if there's no X, because we're outside the principal block here. Oh, that's not actually quite true, is it? So I think I have to put a hat on that X, sorry. Yeah, there might be HOMs between two modules in a non-principal block that factor through projectives, but not otherwise. So here's the conjecture. So what you have to do is not look at those subgroups of the defect group whose centraliser is not p-nilpotent in the group. You have to take the corresponding block of the centraliser and then ask whether it's nilpotent in the sense of Brouet and Pooch, which is equivalent to it being really the representation theory of a P group. And so unfortunately, in order to understand the conjecture, you have to understand Alperin Brouet and you have to understand Brouet Pooch. But let me give you an example, a very concrete example, where I don't know the answer to this conjecture, where you can actually fiddle around with stuff and do some representation theory. So here's an example. So let's take an elementary abelian group of rank 2 in odd characteristic, okay? And let's make a quaternion group of order 8 act on that in such a way that the center of order 2 acts trivially. So it's really a 4 group acting. So you just want to dihedralize each cyclic P. So the quotient by a central element of order 2 is really a product of two dihedral groups of order 2p. So that's your group. It has 2 blocks. The way to see that it has at least 2 blocks is to take that central involution, let's call it T, and look at 1 plus T over 2 and 1 minus T over 2. Those are central idempotents. So the non-principal block corresponds to 1 minus T over 2. So, because that kills the trivial module. So what does that block look like? Well, it was actually determined by John Alperin a long time ago, and that actually led to a lot of trying to understand non-principal blocks in this sort of semi-direct product situation. And the structure is as follows. It looks a bit like a quantized version of an elementary abelian P group. So it has two generators X and Y, which anti-commute instead of commuting, but their P powers are 0, like the generators G minus 1 in an elementary abelian group. So that's the structure of the algebra. It's a P squared dimensional algebra. And we don't really understand its representation theory very well. In particular, what we don't know is, are there finitely generated modules, M and N, whose restrictions to the subalgebra generated by X are just sums of Jordan blocks of length P? That's what it means to be projective. But X of Mn is 0. Sorry, neither of them is free, is what I meant. have to say things the right way around, and that's when standing in front of an audience, that's sometimes not easy. So you really want the support just to be that coordinate axis of the affine plane. So these are periodic modules, M and N, with the same support, but X star equals 0. And I have no idea whether there are any. I've tried quite hard to produce examples, and I've tried quite hard to prove that it can't happen. So there's a little problem. You can actually just sit and, I mean, just take P equals 3. I still don't know the answer. It's a 9-dimensional algebra. Just play around with modules. Okay, so there's a good question for you. And the last thing I want to talk about is cochains on BG. So this is some things I've been doing with John Greenlees over the last few years. So he came up to me, and so I was visiting him in Warwick, and he came up to me and asked me, so what's the singularity category of cochains on BG? What does it look like? And it looks as though the answer has to do with the nucleus. So let me tell you that story. So, I mean, there are many ways of thinking. I'm going to do just cochains on BG with coefficients in characteristic P. So K has characteristic P here. So you can either think of this as a differential graded algebra whose cohomology is the cohomology of the group. So, I mean, for example, you could take a projective resolution and take its endomorphism algebra, for example. That's a good differential graded algebra that's equivalent to cochains on BG. Or there are various higher ways of thinking of it, like an A infinity algebra, whose underlying ring is the cohomology. Or you can think of it as an E infinity algebra, where you look at all the higher commutativities. Or you can think of it as an S algebra in the sense of Elmendorf, Pries, Mendel, and May, in which case it's actually strictly commutative, which is rather strange. Anyway, we want to talk about its derived category. So the objects here are differential graded modules over that differential graded algebra, or A infinity modules over the A infinity algebra, and so on. And the arrows, you take homotopy classes of maps between those differential graded modules. So that is a triangulated category, but you then want to invert the quasi-isomorphisms, the maps which induce an isomorphism in homology. And I have to tell you that the advantage of looking at it as an A infinity algebra or any of these other higher things is you don't have to invert quasi-isomorphisms. For a differential graded algebra, you certainly do. So that's the derived category. And the derived category comes with an action of the cohomology ring of the group. So you may define support in this context and start to study it. So again, you're just looking at subvarieties of the spectrum of the cohomology ring of the group. So we're back in the situation we started with. But you need some sort of finiteness assumption in order to get, in order to start talking about nuclei, thank you. And so Greenlees and Stevenson actually came up with a good definition of the bounded derived category. It's not obvious what to do for a bounded derived category. You don't want to just look at things that are 0 outside a certain region. That's kind of dumb. So their definition is that you look at those differential graded modules whose cohomology is finitely generated as a module over the cohomology of the group. It turns out that has a lot of very good properties and is a really good definition of a bounded derived category. So inside there, you've got the perfect complexes, Namely, those are the ones that you can build in a finite number of steps from cochains on BG. So you're allowed to take finite sums and summands, and you're allowed to complete triangles. Okay, so you might want to think of that as the perfect complexes. For a ring, that gives you the perfect complexes. So the singularity category is then defined as the quotient, the Verdier quotient of the bounded derived category by the perfect complexes. So, for example, you may wonder when the bounded derived category just consists of perfect complexes. That's true if and only if the group is p-nilpotent. Okay, so that's the situation where the singularity category is 0. Okay, still with it? Here's the conjecture. The singularity category is generated by objects supported in the nucleus, but in no smaller subvariety. So the conjecture is that it's generated by objects supported in the nucleus, but for no smaller subvariety is it generated by objects with support in that smaller subvariety. So in some sense, you really want to say the support of the singularity category is the nucleus. And actually, another way of saying it would be the union of the supports of the objects. Well, it's actually hard to say it that way because you have to worry about, yeah, never mind. Let's just keep with this version of the conjecture. So there are other ways of defining support in categories like the singularity category, but I won't go into that. So there's a related conjecture, which is what Greenlees was initially thinking about, which is that the bounded derived category of cochains on BG is generated by some obvious objects. And that for most choices of obvious objects, that's actually equivalent to the object cochains on B of a C log P subgroup, which is an object in that bounded derived category, being a generator for the bounded derived category. So we don't know whether that's true. If it is true, then we can prove that actually 1/2 of the conjecture above is true, namely the singularity category is at least generated by objects with support in the nucleus, but it's not obvious that you can't go to something smaller.
But the conjugate, so all zero subgroups are conjugate. So if you take a conjugate, does it give you a different object?
It gives you exactly the same module.
So just one.
Just one module.
Yeah.
Yes. So this is a single module that generates the bounded derived category. Yes. Yes. Yeah. It's really not obvious whether it generates the bounded derived category. I mean, John and I have actually spent John Greenlees and I have spent many days trying to prove that and failing, and trying to find examples where it doesn't occur and failing and so on.
But that is just known for some class of groups.
Yeah. There's quite a limited class of groups for which we can prove actually all the conjectures I'm stating today. So here's another conjecture which I came up with, which we proved was equivalent to Greenlees' conjecture. It doesn't at all look similar. So here's what you do. You take the stable module category and you take all the modules with no cohomology, and you take all the finitely generated modules. Okay, so finitely generated modules are modules whose cohomology is finitely generated over the cohomology of the group. Right? So you take all the finitely generated modules, and you take all the modules with no cohomology, and you ask what the thick subcategory generated by those is. And the conjecture is that it's actually all modules with finitely generated cohomology. Not at all obvious. We don't know whether it's true, but that conjecture is equivalent to this conjecture of Greenlees about the C log P subgroup. Okay. Are we still with it? Yes, good. Okay, so the theorem that we proved is that those two conjectures are equivalent. And so there are various classes of groups for which the conjecture is true. And one class of groups is where the nucleus is either empty, so the support of the singularity category the singularity category is zero, or the nucleus is zero, in which case the singularity category is very much non-zero, but it's all supported at the maximal ideal. And then John Carlson and I actually managed to prove it in some cases with a nucleus. And those are actually the two groups that I was talking about earlier, and a slight generalization of one. So there are some groups for which you can prove the conjecture, but it was really hard work. I have to tell you that, you take Z mod 3 cross symmetric 3, this 9-dimensional algebra, and you start grinding away, and it just takes a lot of effort to get at this conjecture. It's not a trivial conjecture. I still have a few minutes. Did I have another slide? Yes, I did. Good. Okay, good. So one more situation in which I'd like to talk about the nucleus is compact Lie groups. Okay, and let's just do this in characteristic 0. You can do it in any characteristic and try and understand what's going on. But, it's hard enough in characteristic 0. So let's do that one. So let's say that cochains on BG is regular if the singularity category is 0. Okay, it's a good definition of regular. In the case of rings, it's equivalent to all the usual definitions of regular. So for G finite, it's equivalent to G being p-nilpotent, where that's the characteristic. So let's look at characteristic 0. For a compact Lie group, being regular is equivalent to, you take the maximal torus and you take the normalizer, quotient out the maximal torus, and you want to know whether that acts on degree 2 homology of the torus, let's say with complex coefficients, as a group generated by reflections, pseudo-reflections. So that's actually equivalent to cochains on BG being regular. And so a graduate student of John Greenlees called Pierce managed to prove the following theorem. He proved that in characteristic 0, the union of the images of the subgroups that whose centraliser is regular, subgroups whose centraliser is regular, the images of those is equal to the support of the singularity category. So I think this is quite a good theorem, so John Greenlees and I were both in Bonn a couple of years ago, and we were sitting on a train coming back from Köln, where we had an extremely nice dinner that one of the people in the audience contributed to paying for my dinner. It was my birthday. So John Greenlees and I were sitting in the train on the way back from Cohn to Bonn and actually came up with this as a conjecture. And Greenlees' student was managed to prove it. So I think that's pretty good. But you know, we don't know what happens in other characteristics. I'd like to think that the same thing happens, but then we don't know which things are regular.
In this theorem,
Yes.
you take D to be just the maximal torus, that's not enough.
No.
You
need to take all tori and look at their centralisers. I mean, it may be that this support is small, in which case you need to look at small tori. Yeah. Yeah. And that is the last slide. And so thank you very much.
Going back to the beginning, so I might be getting this a little wrong, but at the very beginning, you define this nucleus. For principal block, you run over subgroups which are not p-nilpotent, p-nilpotent. But when you're doing this for non-principal blocks, you shift to rather considering blocks or going over blocks which are not p-nilpotent. Is there a way of
well, I mean, you're really looking at subgroups where there's corresponding block of the centralized. I mean, if you're in the principal block is p-nilpotent if and only if the group is p-nilpotent. Does that answer your question?
Yeah.
Yes, good.
So, hang on. So, is there product, if you take product of two groups, finite groups, is there a relationship between their nuclei and the components?
Never thought about that. No, so there isn't. I mean, take cyclic 3 cross symmetric 3.
Yeah.
Both have 0 nucleus, but their product has a nucleus.
You mean empty nucleus?
0 nucleus, yeah. 0 or empty, yeah. Both of the factors have 0 or empty nucleus, but the product has non-zero nucleus.
Okay.
In the last slide, we talked about the D groups and about the p-adic groups that you also asked.
P-adic, that's a very good question. I mean, you know, the good thing about this definition is that everyone has their own favorite triangulated category. And so there's a question for everyone in the audience. And it's a different question depending on who you are.
trying to trace for some of your definitions, but could you say what the difference between 0 and empty nucleus is in terms of the module?
Yeah, it's really a question. So if you look at the bounded derived category instead of the stable module category, it's a question as to whether there are complexes of modules that are not perfect, but are equivalent, but are what is it? Not perfect, but still have no cohomology. So, is that right? I think that's right. So you have a perfectly good theory of support for the bounded derived category, and the only difference between that and the stable module category is you have one extra point, namely the origin. So if you think about my original definition for the bounded derived category, that will tell you about the distinction between empty and the origin. Does that answer? Yeah.
All right, if there are no more questions, let's try again.